Okay, we're recording. So I will hand things over to Group 11, and I'm not even going to try to pronounce the title of your group. I'll let you guys do that.
All right, we'll go ahead and get things started then. Thanks everyone for showing up. Good afternoon. So we are Group 11. Their name's Chrysolicatos. It's inspired by Artemis's bow, since we're trying to launch stuff out of the Artemis rocket. So just to kick things off, a little bit about us. We're a team of undergrad mechanical engineering students at the University of Florida, and we're going to be presenting our design for a canisterized satellite dispenser. It'll be used for housing and launching 12U CubeSats nominally from the Artemis 3 mission. So just a little outline of what we'll be going over today. We're going to start with looking at the Hedgehog concept, kind of inspired our design philosophy, and then we'll go through breaking down the analysis of our systems and the details of the design, and then we'll look at the economic viability of the design and the production run. So our Hedgehog concept is focused on simplicity. Our goal is to make space travel, which is inherently a pretty difficult topic. There's a lot of things that need to be considered, accessible to people who are passionate about it. That's our passion, is just being able to understand knowledge of space travel without having like extensive education. And that allows young people, such as students, to get familiar with CubeSats and CSDs and potentially have an avenue to get into space. So with that in mind, we looked at making our design economically viable through just simplicity to make the design cheaper. Less parts just means less cost. So parts like the launching mechanism can be easily substituted if the customer needs changes, money is tight. And what we want to be at the best in the world at is creating a simplistic design, and our team believes that we have achieved that. So we'll get into the details of the design.
How's it going, y'all? Here we have, we can see some pictures of the subsystems that are identified in the CSD, during which the subsystems were split up and worked up among the group and are shown here. Each subsystem performs a unique function that they all work together and provide the essential functionality of the canisterized satellite dispenser. Here we have a product overview. We can get a little sense of scale of how big it is. The CSD dimensions are shown, and we had a motive to stay relatively small in comparison to the size of the actual CubeSat, so we reduce our footprint. We can also see a little bit of accommodations with the satellite or cut-ins and whatnot to reduce weight. And all the casing, CSD, ejection plate, door actuator, and door are the main components, and they'll also be discussed later in the design analysis part. Here shows a rough illustration of the mission sequence of the CSD dispensing the satellite into space. The satellite will be put into lunar orbit to capture photos of the surface of the moon. And once the satellite is in space, the CSD's job is done for the most part. We tried to fit it, fit a small footprint and have accommodations for all the parts, like the railings, which are seen on the CSD, and also gaps to fit the satellite or the satellites, which you can see expanding out in the second stage once it's done.
In here, we have our customer needs for the launch mechanism. It's all for a table for you to see, and the metrics are given next to the needs, and the functions are also to the right of the metrics. And our goal is to illustrate that we reached and addressed every single one of these needs. So for our launch mechanism, we're using an off-the-shelf tiny ejector release mechanism. It is tunable resettable, which addresses needs 1 and 19, which is to be able to test and tune the spring constant so it can change the velocity. And the dimensions fit within the CSDs pretty well. And the ejector plate is what actually pushes the CubeSat. And then dimensions of the ejector plate match that to fit within the CSDs.
This slide is the door mechanism needs that were addressed in this project. And it's just, again, it includes the needs, the metric, and the function. To address the needs that we had, the simple torsional spring and hinge combination opens the door because the door must be operational after being off for 12 months. And then the servo motor with an arm attachment serves as a lock, which allows the door to open within 2 minutes, 100% of the time. The door being made of 6061 T6 aluminum allows for the no debris to be left out into space. And the door does not detach from the CSD, which again means no contamination of the orbital system.
So here are the casing needs, metrics, and functions. As you see, the far right, same structure of the other tables. The far right shows what part of the CSD casing actually accomplishes each of the needs. And then here, so the box shape and cross beams along the wall are what are going to satisfy the structural load capacity and shock load needs. The aluminum material is going to be the weight need, and the load environments, according to the customer needs, are going to handle the thermal, shock loads, acoustic loads, and vibrational loads.
And similar to the other subsystems, we've laid out the needs associated with the CubeSat interface. So how we specifically meet those, that'll be mounted using aluminum rails that will control the center of gravity of the CubeSat satellite system. And the aerospace customer team that we were working with didn't require any communications or fueling connections to their satellite. So we haven't included that. And by doing that, we save some space and save money by not needing to include those electrical components.
So now we're going to talk about some analysis of the casing subsystem. The first one is, should there be a coating applied to the outside of the CSD to help with the temperature and the heat transfer? So an aerodynamic heating depends on how dense the atmosphere is and how fast a rocket ship moving through it is, which means when the rocket is launched, it starts from 0 velocity, and which is in the portion of the atmosphere which is the densest, and accelerates to progressively less dense air. To reduce the amount of heat exposed to the CSD can be coated with a thin layer of thermal control paint. The paint chosen for this experiment was AZ-93. It's an inorganic white thermal paint used for spacecraft and satellite services. The goal of applying a thermal control painting is to increase the emissivity, which is the amount of radiation, and the heat discharge released back to the environment, as well as decreasing the solar absorbance, which is the fraction of the sun's radiation the surface absorbs. If the solar absorbance is higher, there's a higher chance that it adds a heat load to the system, which can negatively affect the system's performance and affect the CubeSat, which is housed inside the CSD. To test the use of the thermal paint, the Stefan Boltzmann law of radiation can be used, as seen in the equation to the right. The Q/T value is the rate of heat transfer. The sigma is the Stefan Boltzmann constant. The area is the surface area of the CSD, which was determined to be all outsides. Since it's a three-dimensional rectangle, it has 6 sides, and the area is found there. The temperature is the highest temperature that the CSD is exposed to, which was found to be 185 degrees Fahrenheit when looking at the different satellite or looking at the spaceship launchers. And then the emissivity with the coating of 0.91 was determined from the website that gave us the AZ-93 thermo paint. When plugging in these values of coating, of using the emissivity with a coat, it yields a rate of heat transfer of almost 1200 joule meters per second squared. When applying the emissivity without a coating of 0.1, which was determined from a MIT study, the rate of heat transfer is around 125 joule meter per second. This is over 9 times a 9-time factor of the rate of heat transfer with coating than without, proving that applying a coating layer is very beneficial for the heat dissipation of the system. We can also calculate the velocity of the CubeSat when it exits. The different variables need to be accounted for as a distance the spring travels from the launcher, which is 0.34 meters, the distance of the CubeSat height, the mass of the CubeSat that's being pushed, which is 20 kilograms, the spring constant, which was determined from the equations to the left. Initially, the kinetic energy and potential energy are set equal. The velocity one is to be determined from equals to k square root of k over m. The force of the spring is using the force of the spring constant, which is k, and x, which is the distance traveled. The force given is 1,112 newtons, which is found from the website manufacturer of the ejector release mechanism. Plugging that in gives you a spring constant of over 3,200. And then using that spring constant to find the velocity yields a velocity of 4.3 meters per second, which is above what the customer requires. The customer wanted a velocity of between 0.5 meters per second and 2 meters per second. To find what force is needed to be applied from the launcher itself, we can change the velocity to 0.5 meters per second. The mass, distance traveled, both stay the same. Rewriting the formulas yields a spring constant of 43.25, which then can be placed into the force equation for springs and yields a force of 14.7 newtons. This force can be adjusted because the ejector release mechanism has an adjustable load. And then similarly, the force for a velocity of 2 meters per second can be calculated. Again, the spring constant can be determined from the velocity of 2, the distance the spring travels, and the mass of the system being pushed. This value is given as 692. And then the force from the spring can be found, which is 235 newtons. Again, this is much smaller than the maximum allowed force from the ejector release mechanism of over 1,100 newtons. So the ejector release mechanisms can properly release the system.
Moving on to the door subsystem. The first analyses we're going to be performing is the load analyses on the hinge. On the exterior of the door, attached will be a hinge that will be screwed in with number 8 size 3/8 inch quarter sunk screws. The importance of these hinges is that they are able to not fall off or be ripped off during at any point of opening. And so to do so, it needs to be counteracting be able to not yield under the spring force of the torsion spring inside that is constantly trying to pry it open. So to find this, we know that the hinge is made of 304 stainless steel, which has a yield strength of 205 megapascals. So the value we have to obtain has to be lower than that. We know that the torsion of the spring is 2 inch-pounds because it's provided by the manufacturer, along with the arm length being 2 inches. To find the force of the spring, we need to take the spring torque and divide it by the arm length times the angle at which it is the sine of the angle at which it's being bent. This angle is going to be equal to 135 degrees. This is because this torsion spring has a resting angle of 225 degrees and will be bent to 90. So when plugging in those values, we obtain a spring force of 1.414 pound force. The other value we need to find for yield to find the stress is the tensile stress area in which the screws reside in. To find this, we use the tensile stress area formula of pi over 4 times the shank diameter of the screw, which is 0.16 inches. And we subtract that from 0.9743, which is a constant, divided by the threads per inch, which is 18 TPI. And we then square that. Plugging in all these values, we obtain a tensile stress area of 0.0088 inches squared. Then we may take all these values and plug them into our stress equation of the spring force over the tensile stress area, and we obtain a value of 160.64 psi or 1.107 megapascals, which gives us a very high distance apart from the yield stress, ensuring that these screws will not be torn apart from their hinges at any point during travel. And even then, we don't believe that the max torque of the spring will be used, so it's even a safer value to calculate.
Okay, so for venting analysis, we have 4 vents around the edges of the door. We looked at venting just for our CSD compartment because we weren't given any specific venting requirements from the aerospace team. So we looked at the ascent venting profile from the Electron launch vehicle from Rocket Labs because it had a more extreme depressurization rate than the SLS rocket. So we put the pressure differential across the walls of the CSD. We found that using the ideal gas law for air and conservation of mass through the vents. So see, we have this equation here in terms of the pressure rate, which is the rate of depressurization from the launch vehicle, the gas constant. We're assuming that the temperature is just a standard temperature. We found the volume within the CSD by subtracting our internal volume and the volume of the actual CubeSat. And we estimated the discharge coefficient of our vents based on looking at orifices of a similar shape and design. And the initial pressure P naught was given in the ascent venting profile. That's the pressure in the compartment when the most extreme rate of depressurization occurred. And doing this, we found that with the vents we have, the pressure differential between the inside and the outside of the CubeSat is going to be about 1/10 of a Pascal, which is really low because our vent area is pretty high relative to the volume inside the CSD. And we did that so that if we're working with CubeSats that do have venting requirements, we'll be able to accommodate them as well.
So next, we're going to be talking about the servo motor arm. So in this analysis, here's a little diagram explaining how it's going to function. Essentially, the servo motor arm is behind this diagram, and there will be a lock on it that turns to unhinge. But it has to be able to overcome the force of the door opening and the torsion spring pushing on it. So we need to ensure that the torque of the motor is high enough that it will do so. So the distance at which it's acting from is 1 inch or 0.0254 meters. And so the first thing we need to calculate is the door force. And while in space, the force of the door is negligible, we still have to account for it here on Earth when it's like in operation and sitting to ensure that nothing breaks. So we found the mass of the door to be 0.244 kilograms. And the distance at which it's applied, again, is going to be 0.0254 meters. From that, we find the force to be 2.393 newtons. And we can just plug in the distance to find the torque of 0.0607 Newton meters. We're then going to add the two torques of the door and the spring, which we found the torque of the spring in the hinge load analysis to be 1.414 pound force, which converts to 6.2916 newtons. Combining those two values, we get a total torque of 0.2867 Newton meters. We then need to find the total force that is being acted on from the torque using the distance described earlier of 0.0254 meters. So we find this by dividing the torque by the distance to get a force of 11.287 newtons. But we still need to account for the friction force, as both the lock and the latch will be made of 6061 aluminum, which needs to be lubricated to ensure no cold welding occurs between the two objects. And that provides us with a friction force coefficient of 0.3, which we can then multiply by the total force we found of 11.287 to find our friction force of, which is approximately 3.386 newtons. We can then take the distance of application to find our friction torque, which is going to be 0.08601 Newton meters, which is clearly within range of what the arm is capable of, with its max torque range being 0.5 Newton meters. So that gives us about a factor of safety of about 5 that we can work with, meaning that the lock will be easily able to deattach as long as we make sure that we lubricate the latch and the lock interface.
Of course, it's very important to acknowledge that the load experienced by the walls need to be able to withstand whatever is being applied during the launch. So we did a hand calculation for the wall, and we treated it as a simply supported beam. So this is just one wall of the CSD. And according to the customer needs in the axle direction, a shock load that we would experience is around 3 Gs. So multiplying that by the mass of the wall, we get a value of 3.76. And this is treated as a distributed load throughout the beam. And with the given values of 10.04 and 0.06 and 14.6 inches for the base height and length, we can find our moment of inertia, which comes out to 0.05 inches cubed. Using this value, we can then find the bending stress. Now, the bending stress is important because we don't want that to ever reach the yielding stress. And we will be using the yielding stress because it's important to make sure that the aluminum doesn't yield. And according to our calculations, it never does. And that brings into the question, what is the max moment that can occur when in space? So plugging in everything, our geometry, we can get a max moment of 58,000 pound force per inch. And this is much higher than any experienced moment that is according to the customer's needs, whether that be the shock load or vibrational natural frequencies that can be experienced throughout space. The geometry of the CSD is just fine the way it is. And now we have our design highlights and key features. There's a couple things that we wanted to illustrate to you guys. And some of them include the resettable launcher. Can you go back, please? Thank you. It's the one thing is the ease of use in the launcher. So one thing that we have to focus on is the reliability of the launching subsystem. It's important to make sure that's reliable. And the only way for us to make sure it is reliable is through testing. And the resettability of these launching mechanisms makes it so it's easy to rerun these tests and make sure that we reach our desired velocity and we can tune them properly. Another design highlight is our space for the solar panels. We don't allow much leeway when it comes to putting in these CubeSats, but we do acknowledge that a lot of these teams need space for any extremities that are outside the CubeSat normal dimensions, and that's what we applied here.
Some other design highlights include the rails. The aerospace team known as Celine, they designed their CubeSats with rails to allow the CubeSats to be constrained in the X and Y axis, along with getting a straight path for its ejection. The frame of the CubeSat is made of 775 T6 aluminum, and while the rails are made of 6061 T6 aluminum. And we are assuming that the rails will be anodized. But since different anodizing processes produce varying surfaces, the rails will be lubricated to decrease the coefficient of friction, which also reduces the effect of cold welding, which is not desirable during the duration of the mission. And another design highlight are the mounting flanges. Initially in our first design, we only had 2 mounting flanges, but after performing a load analysis on the CSD, it was determined that having 4 mounting flanges to distribute the load on the CSD would be much better, as the holes were added to make sure they match the connection points on the payloads. And this also allows for flexibility in terms of location mounting.
And one last highlight is the connection holes. These are not something that would be applied often, but sometimes in some missions, some aerospace teams would like to stack CSDs on top of each other. But even if no one's going to stack the hole or the CSDs together, the holes themselves also just reduce the weight by a little bit. Maybe not too much where it matters, but it is something to acknowledge. And then we also have these cross beams, which have changed the natural frequency of the walls. And that's important because we don't want the walls to match the natural frequency that's excited from the launch. And then we have our access panel, which gives us easy access to the interior of the CubeSat if that's necessary. The goal is to never touch the CubeSat, but given the opportunity, we made it easy for anyone to just access it. And then other key features that, because we use the tiny ejector release mechanism, it reduces the complexity. Like, again, our goal is to be as simple as possible. And technically, our entire back panel is modular in terms of it can be easily edited. We can add any holes. You can thread any holes that you want on it. If you want to change the release mechanism, you can do so. There's no problem that there's nothing set in stone when it comes to making the back panel. And there's also minimal contamination when it comes to launching in space, because the only thing that's getting launched is the CubeSat and the ejector plate.
This is just an exploded view of the overall system and how you would assemble it. You have your casing all the way to the left. The first couple of things you would put in is the power supply, as well as the launch ejector launch mechanism, followed by the launch plate. Then you would include the servo that opens and closes the door, as well as the door itself and the access panel.
So that pretty much sums it up for the actual features of the CSD. So the next big question to address is the actual cost of everything. So when manufacturing a prototype for the design, it was determined that the ERM, the ejector release mechanism, was going to end up being way too expensive. Similar products were about $5,000 to $7,000 price range. So for a prototype system, we are using a different spring system that will output the same amount of force that we want. So it'll prove that the output force will work, and the ERM is already tested and validated through the company. So that severely dropped our OTS part price down to only $227. The raw materials is $204.74 because we decided to go with a casting method over taking like a large 8x8 by 2 feet billet of aluminum and then just take out all the interior. Because we're doing the casting, manufacturing cost, primarily labor, isn't really associated with it. There's very little, it's a non-labor intensive process, casting. So it was determined that the manufacturing labor cost wasn't included there. Energy was determined for each process to reach the necessary temperatures to melt down the aluminum and to cast it, and then the actual machining to fine tune all the dimensioning after the casting has been done. And assembly was completed using the Boothroyd and Dewhurst assembly times, and then using information from the Bureau of Labor Statistics to determine how much assemblers are paid hourly. And that includes the cost for overhead and benefits for the employer, averaging about $63 an hour, times about the 3.5 minutes it took to actually assemble each unit. So our prototype came out to about $450. Then the OTS parts, now for the production run, this was for a total of 50 units, which based off of the upcoming number of launches that NASA has, about 23 that they've announced so far, I believe. That was a little over 2 on each system. So this includes the ERM now, and it includes slightly more sizing and raw materials. But the actual manufacturing, energy, and assembly costs are 1-to-1. It's just the same cost times 50, because all of the actual manual labor, the custom parts, are being made the exact same way in the prototype and the production, which will allow us to get a more realistic view of how the casing and how casing door and the access panel all perform in the real scenario. So that came out to a total of $367,000. And that also doesn't include any type of benefits we could get for ordering in bulk. So making an order of 50 ERMs, we might get a 5-10% discount, and that could severely drop the price another $10,000 to $25,000. And then here's just a comparison of the actual pie chart showing what part of each prototype and production actually make up each of the total cost. And it shows that by far OTS in both systems was the main contributor. But in the prototype, it's kind of split 50-50 between the OTS and raw materials, with very little cost in actual manufacturing, energy, and assembly. So as you can see here through all of the different subsystems, it's a very simplistic, easy to use system where it's primarily controlled by just a few signals to launch and open the door. The calculations showed that it meets all of the required customer needs with a decent factor of safety for each of them. And the budget is under the allocated amount. So as a company and the customer, we would both be saving money, and it would make ourselves more inclined, or the customer more inclined to choose us, because we would be able to give them a better pricing for a CSD. And I think that's it. So thank you.
Okay, great. So we've got about 15 minutes left. Normally I say, panelists, are there questions? But I need to ask a question first, which is, if you guys go back to your heat transfer analysis, what's a joule meter per second?
When I was searching for the law of radiation, that's what it gave me as a unit. I'm pretty sure it should be power, but
Joule meter per second squared. Okay. Okay. I need to think about that a little bit more. So rate of heat transfer, it's watts, right? So the question is a joule meter per second squared convert into watts, and I gotta actually run through and see if everything cancels. So I've never seen that unit before, so that was surprising to me to see that. So I'll work through it. The other thing that I wanted to ask, you guys might have made this assumption, but you didn't say it. There's a pretty big assumption inherent in here, which is, if you guys remember back to your heat transfer class, this equation that you're using is assuming that you're basically radiating to an infinite sink at 0 Kelvin, right? Is what this means, which might be true for, or well, not true, but a reasonable approximation if you're radiating out into space, right? Space is a few degrees above 0 Kelvin. But how does that change the result? And also you're not in deep space, right? You're basically in orbit either around the Earth or the Moon, or in transit between one and the other. So you've got like, you know, really big celestial bodies that you're actually radiating to. So does that?
And the rocket itself.
Well, yeah, oh yeah, yeah, and a big rocket too. So is the assumption that you're basically radiating to black space at 0 Kelvin, is that correct?
That's what I that's what I use for the calculation. Yes, we are in orbit still, and you are like surrounded by other planets and other bodies, which could have effect on it. The main part of this calculation was really just to show that the emissivity with a coating is much higher than without a coating, and that using a coating on the exterior of the CSD has a big impact in the the rate of heat transfer.
Okay, yeah, I mean, I get that, but also you could just look at the emissivity, right? And you could compare the emissivity of non-coated surface versus coated surface, and that would give you the same information, I guess. So then to kind of follow on to your point, did you guys then take this number, and I'm still not sure about the units, but did you take this number and propagate it into something that would be meaningful for the CSD and the CubeSat, like what's the internal temperature when you're out in space? Is that what this I don't speak Fahrenheit, 458 Kelvin is that?
That's we looked back to the customer needs, and when we were quantifying metrics, and the metrics for max temperature found is between 185 degrees Fahrenheit and negative 121 degrees Fahrenheit. And I just took the absolute maximum to find the absolute maximum or the absolute temperature to max temperature to find.
Oh, okay. I think I see what you're doing. Okay. So you did this. In my mind, I think you did this in the reverse way. If I'm following what you're doing, you said we are going to assume that the inside of the cube, or I guess it's the surface of the CubeSat, is at about 460 Kelvin, and we're going to let it radiate to space at 0 Kelvin. And how much heat transfer do we get with a coating and without a coating?
Correct.
Okay.
The temperature was picked initially. Yeah, the temperature was chosen initially based on the customer needs and our quantifying metrics, looking through different spaceships and seeing how they, like, what the maximum temperature they feel.
Yeah. So is it actually going to work that way?
No, that's just the maximum. It would probably be less, but that's like the maximum temperature it should withstand.
Okay. Well, I guess let me say that I appreciate that you guys are trying to do the heat transfer analysis, because most of the other groups just sort of, you know, anything that's energy thermal fluids, they sort of brush under the rug and hope I don't notice. So I appreciate that you guys tried to do this.
Yeah, I'll take a look at it again, and I'll see where all the numbers come from. And
yeah, I think you want to. I think you want to think about it in the opposite way, right? It's not that the CubeSat is going to be sitting at 460 Kelvin, but it's what's the steady state temperature of the CubeSat and the CSD, if it's allowed to like radiate to the surroundings, you know, whether that's space or the rocket body or the planet or the sun or whatever, like what's the steady state temperature?
okay.
And then is that steady state temperature, after you allow all this radiation to happen, within the bounds set by your customer needs? So I think that's the way you want to approach it, rather than using those temperatures and then trying to figure out how much heat transfer happens.
Okay. Yeah.
So
I'll flip it around.
Okay, cool. So I'll leave you alone now about heat transfer.
Yeah. Thank you.
Let me hand things over to the panel. So Tom or Sydney, if you guys have got questions.
Yeah, guys, this is Tom Singer from Northrop Grumman. Towards the end of the presentation, maybe you said earlier, I missed it, but I think you said you're going to cast your box. Is that correct?
Yeah, so I was just for the cost wise, originally we were gonna take that, it was originally a 10 by 10 by about 2 feet the aluminum bar, and then just take out all the interior because it's practically a shell. And it ended up costing, we were
Okay,
gonna
yeah,
end
I'd
up spending
say
over
that's
$1,000 wasting.
yeah, that's a bad idea. I wouldn't do it that way.
Yeah.
So what
Uh,
drove you to cast as opposed to just assembling some flat plate with some angles?
There were some concerns about with Professor Generali about adding fasteners and also welding. Those are the two that we considered in our design review 1. And we thought about it and we did more research, and we just thought if it was just one piece all around, it would just be much better for our purposes.
it would also make a little more difficult, in my opinion, to keep the symmetry between the rails. You might get them uneven because they're gonna basically pop out as a flat line or like a little notch on top if you were to make it as one long sheet and then bend it. So you'd really have to make sure that you had a even rail on each side. So I think it would
Yeah,
make it a little more complicated on that.
Yeah, casting strikes me as the wrong thing to do here. Casting is typically great for kind of big, bulky parts, but for things that are basically thin plates, that it tends not to be the way to go. Let's see. You were early on, and one other comment here is add slide numbers so we can refer to things when we're going back to this. But early on, when you're talking about requirements, I think you had mentioned like a factor safety / launch reliability of 1. Can you explain what that means?
That just implies that it was gonna go out every single time.
So you
There's not really
a probability of failure of 0.
Correct.
Yes.
How much
better.
is your customer willing to spend to achieve a probability of failure of 0?
Depending on who the
Because
contractor
a guy over the wall of my
customer is.
cube just said an infinite amount of money, and that's basically correct, right? I mean, a probability of failure of 0 is unachievable, and you know, if we wanted to achieve it, we would spend a lot of money doing it on like you know, human rated systems and not a CubeSat launcher. So that strikes me as a poorly defined need, and I'm not sure exactly what the factor of safety has to do with the launch reliability there, but something is severely off with that.
Yeah, we took that from the customer needs given from aerospace, where it said 100% launch reliability on their customer needs that were provided to us.
Yeah, that was given to us from the semester, but that started the semester.
Yeah, I guarantee you, you're not going to achieve that. And I wonder what your factor of safety requirement actually is for your, you know, like structural analysis. But as an overall system, you know, you're never going to achieve 100% reliability, right? And you don't need to achieve 100% reliability, right? You're launching CubeSats. You know, these aren't high dollar, you know, defense projects with, you know, billion-dollar budgets and, you know, need as much reliability as they can get. I mean, I don't want to say they're throwaway items, but you know, it's not something that people are spending $1 billion on a single CubeSat. So I think that is severely the wrong requirement.
Just to jump in, that actually did well. And so that was the requirement from Professor Generali, who's representing NASA, and it might reflect that, you know, he loves this project, and so wanted to make sure that the door opened.
There you go. Yeah. So think about that a little bit. You gave an analysis with you know, the deployment velocity and the distance you had to achieve that velocity in. Did you consider the acceleration load that's going to impart, and is that acceptable to the customer?
Do you mind going to that slide for me, please? So the ejector launch mechanism can be max loaded at 1100 newtons, and then we would want to that the velocity that is given at 4.3 is too high. The customer wants between 0.5 and 2 meters per second, so we'd have to we'd have to tighten. There's a tool that can be used to change the amount of force from the spring, so we can lower that to meet the customer need of between 0.5 and 2 meters per second.
Okay, but from an acceleration standpoint, right? The acceleration is what's going to load up the CubeSat, and presumably they would like you not to accelerate them at 3,000 Gs or something absurd like that. So did you consider how quickly you're accelerating your CubeSat on its way out and what your customer requirement is?
I did not consider that, but I did not
So
find it.
when we met with the aerospace team, they had told us that as long, I don't think they really gave us a requirement as to what the CubeSat itself needed to have as an acceleration. For what they had said was that we just had to get it out at 2 meters per second, and that they could control it using some onboard system that they have on their CubeSat for controlling the
I'd just
trajectory.
be concerned, and I don't think it's a practical, or I don't think it's a concern necessarily for your system, right? Because you're accelerating over a third of a meter, right? So that's plenty of distance. I think the team I saw earlier was accelerating over like 5 centimeters, and that's like an 8G load, right? Which is maybe survivable, but maybe not, right? I think you guys are going to be in the range of like 1.5 G or something, which is probably fine. But it's something to compare against customer requirement. I mean, as a interface requirement, I'm sure that your customer is going to have some requirement for what their satellite can withstand that you need to be able to meet. So consider that. How is and so speaking of that, how does the CubeSat actually mate with your design?
So it just we have the railing system in there. So
does it just kind of like nestle snugly in between the rails?
Exactly. So it just kind of hugs onto the rail system. It'll rest on the bottom two, with the top two kind of keeping it for an alignment. It's not necessarily like a press fit type of squeeze it in there.
You said it's going to rest on the bottom two and
on the bottom two rails, and the top two rails are going
picture?
to keep it in an alignment. It should be in there somewhere on one of the CAD models, Justin.
Okay.
Is there other ones that you could see the rails a little better? Because
there's
kind
one
of
here
hard
at
to
the
see with the
end.
shadows. There you go.
Okay, so you've basically got like 4 rails along the corners that are
correct.
very
One rail in each corner.
precisely located so that they meet some tight interface control with the exterior of your CubeSat.
Yeah.
Correct, and they're also used to keep it a bit of an alignment towards the actual trajectory of launching it outside, launching the CubeSat.
So what holds the CubeSat axially? Like along the axis of those rails, right? That's not providing any constraint in and out of your container. Is it free to just kind of shake in there?
You're saying like the Z direction, or just to move around?
If the Z direction is in the direction out, then yes.
Just
what constrains it in the Z direction?
Okay. I believe the ejection plate and the door are measured up with the 12U CubeSat so that they no more than a couple, maybe a millimeter or two. I could be wrong, but that's
what.
So is the CubeSat free to just sort of shake in that 1 millimeter distance?
I don't believe so. Right, Alex, that was the CAD stuff.
No, it shouldn't. On the CubeSat model, there were contact points for the door and ejector plate on the ends, I believe, for the later iteration in the Aero team, and it fits in between the ejector plate and door flush. That can be changed if needed, but it shouldn't shake in the Z axis or move.
Okay, I'd be concerned that there's not some sort of positive connection, and what's the dynamic environment going to be on the satellite? If it's free to move even a little bit, right, then the dynamic vibration environment is going to like shake the CubeSat maybe severely, and I'd be concerned about that. While we're looking at this picture, why is your door actuator located where it is? That's also the latch system, right? That's the system that holds the door shut and then releases it, and then the spring pulls the door open, right?
Yes.
So why is it located there?
It was located at the front just for ease of assembly because it can be put right in the front with the door. And there's also a latch on the door, which that's what actuates. But it was mostly just for ease of assembly, and it was a good spot for it.
Wouldn't it be more effective if it was further away from the hinge?
Yeah, I could, yeah.
Yeah, I think it would. Let's see, you'd mentioned that you've got these holes on the sides of your walls for, I guess, some sort of modularity and stacking of containers.
Mhm.
Is that a customer requirement? Because if it's not, I
It is
think not having those holes would be preferable from a complexity of manufacture, from a stress concentration point. I also don't know how you're going to stack these if you have the flanges that want to occupy the same space.
Yeah, those can be reduced or just moved out completely.
Yeah. Let's see what else I have that I wanted to mention. You had it on your cost analysis. I think you had an assembly cost of like $3 for your prototype version of this.
Yes, for the actual assembly.
That strikes me as extremely. That's the cost for labor for somebody to put this together.
Per unit, yes. It was
Oh, man.
determined I believe it was 16 or it was $18
So
an hour based off the Bureau of Labor Statistics hourly, plus 200% of the hourly wage was for overhead and 50%
Mhm.
for benefits included for the benefits of the actual
Right.
employer.
So you're somewhere in the neighborhood of like $50 an hour for assembly.
62.
And you think this is going to happen? Okay. So and you think this is going to happen on the order of minutes?
Based off of the insertion and handling charts provided by the Boothroyd and Dewhurst assembly time method, it came out to 227 seconds, I believe, to put together everything.
That's awfully quick to assemble space hardware.
Yeah, so there is obviously plenty of room in that budget. There's a whole $50, so that, I mean, it could take up to an hour and we'd still be under budget. Which I did mention. I think it's mentioned in our final report that there is plenty of space in the budget that even maybe that's a best case scenario. It'll take them 3 minutes, 4 minutes to put together. But because of the actual room in the budget, it could take them up to an hour, and we would still have space in our budget to stay under the $500 for the prototype.
Yeah, I'm not too concerned about the overall effect, but it just strikes me as that's comically low for space hardware. But granted, you're doing a prototype and you're not going to do all the quality control and stuff that you might do on a full up thing, but being able to put something together that is presumably going to have power connections for the internal CubeSat and all this other stuff. I can't imagine that somebody could do that in under 6 minutes.
Yeah, it was. So the way the time handling comes into it, so most of it is the casing, the door, the access door are in the way that the timetable works are like 6 seconds to grab it and put it on a table. And the majority of things like screws are just in total it says about 3 seconds to put in each screw, which are the main components of putting together the whole system. Is kind of just.
Yeah, I don't think anybody's putting a screw in 3 seconds, especially
right, exactly.
On the order of these sizes, right? The small screws are going to cross thread if you try to put them in too quick, and that, I mean, it's just it's unreasonable. So I don't know exactly. I've never dealt with Boothroyd and Dewhurst, but they got this wrong. So I would rethink that.
Okay, thank you.
Can I answer Sydney's question? Saw in the chat. The application of the radiation protection and the wait time for drying considered. I don't think it was, because there's nothing in the Boothroyd and Dewhurst about spray painting something. But to be fair, once everything is made and assembled together, the spray paint the paint is the last thing. The coating is the last thing to do. So I don't know if that's like physical labor costs, and I guess I don't know if I would be considered part of the assembly time for the drying, but maybe the process of actually applying the coating should be considered. And we can add that.
I can say I think
experience.
application maybe, but wait time is, I don't know that there's really reliant on any type of person. As a business person, I wouldn't paying somebody to just sit there while paint dries.
Yeah.
But definitely the application of the radiation protection is something to consider. It's just not mentioned there. The Booth Road and Dewhurst, I have it open here. It mainly talks about just like insertion of screws and fasteners and stuff, mechanical fastening process. So like some of the stuff we were saying, it says screw tightening immediately after insertion should take a total of about 5 seconds for a typical screw on the system, which is probably why it's severely under cost, as you said, Mr. Singer.
All right, and then
I have
one more just, oh, I'm sorry, Sydney, if you got stuff, go ahead. I've got one more, but I'll hold off.
I was just going to reiterate with the casting, just how big of a process that is. With casting, you have to make the mold, A, and B, take it apart, which takes time and wait for cooling. Did you consider the cost of a mold at all, or even what type? Are you going to do like sand casting, a metal casting? Because all of those
Yes, so
have additional requirements.
yeah, so I considered a sand casting mold, which I saw for more simple parts could range to up to about $500. For simple parts, not up to, it ranges on the low side of about $500 for a mold. However, I figured if there was a way to cast here through the university, that would be less on the actual pricing side of it, because it's already stuff that we have and the capabilities to do. But for the full production run, we would I'd imagine outsource, it'd be difficult for the university with, especially all the other students and everything using it, to prototype 100 or 50 of these systems. So at that point, I would include the cost of the sand casting method onto the production method.
Okay, cool. Mr. Singer?
Yeah, so the one other thing, when you were doing the analysis of the stress in the bolts, this is on, I guess, on the door hinge.
Yeah.
There we go. Is this spring force? Are you doing basically spring force over the area of the tensile stress area of the bolt?
Essentially, yes.
Yeah. So where is that spring force? Is that the force that's opening the door?
So the torsion spring is bent at 225 as so, and then it'll close with the door like this. So it'll be constantly trying to push on the door like this. So that's the force I calculated. And those are the formulas I found. It said torque is equal to the force times the arm length times the angle at which it's bent. The sine of the angle which it's bent. And then I'd
kind of like to see a free body diagram of how that spring force gets transmitted through the fasteners, because I don't think I'm understanding that, and I'm not sure that I fully believe that the spring force that's being calculated here is going to go through, through the bolt, just as a one-to-one kind of deal. So I think a free body diagram would help greatly with communicating that.
Yeah, the intention of this analysis was to just find the place of most likely failure, and since the the screws they don't have that much depth to them because of the spacing allowed in the CSD, that's most likely where it's calculated to fail. But I definitely agree with what you're saying, that there are a lot of different places where the force is distributed beyond just directly translating into the screw.
All right, so that's all I've got.
All right, and good timing, because it's 3 o'clock and we've actually got another final oral presentation that starts in 1 minute. So good time to wrap up.
Really quick,
I-
guys. I don't know if I missed it. How much does this weigh?
In total, I think it weighs 4.8 kilograms. So about 200 grams under the requirement of 5 kilograms.
Great.
I also just had one quick question, Mr. Singer. So earlier you had mentioned casing you don't think would be the right way. It was expected in the calculations to oversize the casing, the molds to about by 15%, and then to bring down to the actual dimensioning. Would you still not
So
recommend
you're
it at
gonna do
that point?
machining after casting, right?
Correct.
Yeah, I mean, that's more work, more labor. So I mean, that's coming out of your $3 budget for labor.
Right.
Yeah, I many reasons why I don't think casting is the right way to manufacture this.
Okay. Thank you.
Okay, great. So again, we just ran out of time, like officially, because I'm now getting summoned to the next meeting. So let's wrap it up there. But my parting thought is just to thank you guys for sharing your design with us, and for a great presentation, and for a good semester. We've come a long way from April, or not April, from August until now. So it's been great to, kind of watch you guys, especially, this group, as you guys know, had how to put this, just some struggles with team integration, and hopefully those have been kind of resolved and overcome, and you guys have found a good cohesion in terms of your teamwork. It seems like now that you guys you've all got the same backgrounds, and the presentation was very well coordinated. People had their subject areas. You were passing from one to the other very seamlessly. So at least outwardly, you guys have done a really good job of making it look like you've discovered your team cohesion. So hopefully that's true both outwardly and inwardly. So anyway, with that, let me hit the record stop button.